All right, hello everybody. My name is Jordan Larson and I will be your host this afternoon on NASA's Technology Transfer Program webinar on the NASA's Integral Tuned Mass Absorber for Turbine Blades. I would just like to thank everybody for spending your afternoon with us, whether it be your lunch break or just your afternoon here today. We just really appreciate it. Thank you so much. Our presenter today is Dr. Andy Brown. Andy received his BS in Mechanical Engineering from Duke University and his master's and doctorate from Georgia Tech in Mechanical Engineering. Andy has had a long and successful career here at NASA Marshall Space Flight Center, where he's worked mainly on rocket engine dynamics and loads research, development, and production analysts. Presently, he is supporting structural dynamic analysts of the Merlin engines for the Commercial Crew Program and the RS-25 engine, which powers the first stage of the Space Launch System. And he is also currently writing a book on the structural dynamics of liquid rocket engines. Following Andy's presentation, I will give a brief description on how NASA licenses technologies to outside organizations. But before we get started, I would like to point out that your microphones will be muted throughout this presentation. So if you have any questions, please type them into the chat box that's located in the lower right corner of your screen, and we will answer them during the Q&A session at the end. And with that, I'm going to go ahead and turn it over to you, Andy.
Well, thank you very much, Jordan, and thank you, Sean, for setting up this. Thank you all for attending. Looks like we have a good group here. And on our opening page, we have here a view of the Space Launch System, which is actually as it is right this moment. If you were to look up, I guess the wet dress rehearsal was yesterday. And this innovation that I'll be discussing today could be put into a rocket engine, or it could be put into one of the myriad of other applications of turbines. So the motivation for this innovation is to avoid high resonant response and high cycle fatigue, which is a major concern of the $100 billion worldwide turbine industry. And the turbine industry ranges from power generation. Turbines actually make 75% of all the power that's used around the world, to jet engines, to rocket engine turbine machinery. And the thing that is a big problem is failure of the turbine blades. And the turbine blades are what drive the entire turbine. It drives in the rocket engine, it drives the pumps. In jet engines, it drives the jet mechanism. And in gas turbines, it creates the power. And in all of these things, blade failure is potentially catastrophic. Now, there has been a lot of success with preventative measures, but they are quite expensive. Now, one thing that, this is a view here of an Ssme turbine blade failure that was during the development of the Space Shuttle main engine back in the 70s. And you can see here a lot of broken turbine blades. Now, this was called an inserted bladed disc, where the turbine blades were inserted into a disc. And so you had 100 or so of these turbine blades and all kinds of different parts that you had to keep track of and manufacture separately. Now there's been a move towards Intraglybladed discs, which are called blisks. And this reduces the part count, it reduces the manufacturing costs, and it actually even increases performance. But one problem is that there's no interface between the turbine blades and the disc anymore. Here, before, there was a mechanical interface between the two, which when they jiggled, when the blades jiggled under loading, it would provide damping, which would reduce the resonant response. So with these blisks, where it's a single piece, it's a single disc with blades machined out of it, you no longer have that damping. So that has exacerbated this problem. Now, NASA is a member, along with other major organizations around the world in turbine machinery and turbines, in a consortium called the Guide Consortium on Turbine Aeromechanics. And our organization puts out a request for proposal every year. And this past one, from that, we mentioned that there's a large demand for the development of an effective damper for blisks, that higher order modes have little vibration of that disc. So with turbine blades, you have low order modes, fundamental modes, but then you also have higher modes at higher frequencies. And traditional under platform dampers just can't dampen out those vibrations. One thing that about implementing vibration control technologies is that they should be manufacturable. If you come up with a solution, you can't build it, what good is it? And finally, additive manufacturing is a new development that really could help out developing some damping concepts. Let me show you some other motivation now, or why this is so important. Back in 1996, there was a Delta Airlines flight, and an engine exploded during the takeoff, and the pieces of the engine actually went through into the fuselage. And there was the failure of a fan hub, which was caused by a fatigue crack in the fan blades. And a similar thing like this happened with the Southwest flight recently. And then also in 2017, an Air France flight had uncontained engine failure due to fatigue cracking. So let me tell you about the project itself now. This is the project. Basically, this is an innovative concept using a tuned mass absorber that is integrally fabricated into a cavity inside the turbine blade airfoil using additive manufacturing. And tuned mass absorption is not damping. That's a very important concept. It is not damping. It rearranges the structural dynamics of your system to reduce the response. And the problem with damping is that classical damping is unpredictable. So I have a picture here of my prototype 1. Well, let me go on. The tuned mass absorber that is the innovation has an elliptical cross section and is optimized to reduce resonant response for any two modes. Again, unlike traditional dampers, which are targeted towards generally just the first couple of modes, this concept can target any modes in your structure. And so this has the potential to significantly impact the development and operational costs for both industry and NASA. So just a little timeline. This project began in March of 2019. I received some seed funding, and with this money, I did analysis, and I got funding to develop this first prototype, which I'm showing you here. And if you click on the upper right menu of your screen, the 3 dots, and you say move to stage, you find the option for that, you'll get a bigger view of this video, and you can see a bigger view of the blade here, and this of the prototype. So that's worthwhile. I would recommend that you do that if you can, just so that you can see this a little bigger. And what you have here, this is just sort of a generic airfoil for an impulse turbine. And inside, it's shaped like that cross section of the prototype 1 picture. And so inside is this tuned mass absorber. It's that cylinder looking thing. And it's actually inside, suspended from the top, or cantilevered from the top, and extends downward span-wise. And there's a little hole here, and through the hole you may be able to see, let's see, I don't know if that's too bright, you may be able to see the absorber through the hole. Now the purpose of that hole is just for laser vibrometry measurement. So when we measure the response of this prototype, we shine a laser through that hole and you can actually see the tuned mass absorber moving. So what I've got shown here is also the additive manufacturing right away after it's been fabricated. And you can see that these, that the blades are on their ends. And why is that? Well, I'm simulating how you would fabricate an entire blisk. When you fabricate an entire blisk, it's going to be from that direction up. It's going to be in the chord-wise direction that you fabricate your turbine blades. Chord-wise is this direction, and span-wise is this direction. So the tuned mass absorber for prototype 1 is span-wise, but you're always going to be fabricating it chord-wise because you're building an entire blisk. And I've got shown 2 blades that I actually fabricated. One was a baseline blade without an absorber, and one was the prototype with the absorber, which I have here. Now you can also see a little material underneath the blade, and that's actually a support structure, a scaffolding. And if you're familiar with additive manufacturing, that's required whenever you have an angle of more than 45 degrees. The material can't support itself during the additive manufacturing. So you have to build this scaffolding. And that has come into play here. With what you see, the scaffolding is quite easy to remove. So I tested this first prototype of the span-wise TMA, I'm calling it, tuned mass absorber. And then I received some money to build a second prototype, and then eventually a third prototype. The second prototype has the tuned mass absorber in the chordwise direction. That is the same direction as the fabrication, as shown in this picture. And the reason for that is, well, the span-wise TMA was not self-supporting. And so we had to build inside the blade a little scaffolding. So that's kind of a difficult issue, right? And we knew this ahead of time, but that's just where we were. That's what we'd come up with. So in order to remove the scaffolding, we had built a electrode discharge tool to go into this hole that we actually designed at the top to move in and melt away that scaffolding and then come back out. Well, that worked fine, and it's fine for the prototype. But if you're going to have a disc, a blisk with 100 blades, that's a very expensive step to move in, melt away the scaffolding, and come back out, and then go on to your next blade, move in, melt away. Because each step is not as simple as just me moving my finger in and out. It takes some time, and you have to design this tool, etc. So with this prototype 3 concept, prototype 2 and 3, that's no longer necessary because the tuned mass absorber is entirely self-supporting. You can support up to an angle of 45 degrees, which this angle is less than that. So another advantage of this concept is that you can actually place the location of the tuned mass absorber within the blade anywhere you want, span-wise. So with this prototype 3, and I have a photo shown here, it's placed up near the free edge of the turbine blade because that's where most of your energy goes into the blade, and that's where you're going to get your most absorption, energy absorption. But let's say you had a shrouded blade, which some of you may be familiar with. Well, in that case, you would have the most motion, your blade would be right in the middle. Well, you could place this tuned mass absorber right in the middle. So it's got that capability to put it anywhere that you want. And again, the hole in the front here is just for visualization with your measurement laser. You have two little bitty holes in the top, and that is to blow out the remaining powder after the additive manufacturing operation. So additive manufacturing is direct laser metal sintering, or direct metal laser sintering, and it lays down a powder, which it then lays down a powder, moves a laser over it, and actually melts that powder into the form that you're building up. So you have to blow out the powder that was left in your cavity. So you just blow it through those holes, which is quite easy. So along the way, I had two actually prototypes that looked like this. In there, the tech transfer office at Marshall did decide to pursue commercialization, and a patent was explored, a lot of investigative work to make sure it was legit and applied for. And that enables me to give you a lot of details of the innovation. So what is it that we're talking about here? What are we trying to really achieve? Well, we're trying to reduce the reaction, the response of modes. And I've got here two of the basic modes for this blade. This is called the stiff-wise mode, and it's at 7165 Hertz. And this is called the flex-wise mode, and it's at 7369 Hertz. And here again is a photo of the real thing. So these are computer models just showing you the mode shapes that you're going to try to attack. Now, what is it that tuned mass absorbers do? when you put a tuned mass absorber into a system, and this is a physics that has been around for a long time, it splits the mode that you've got into two modes. In one mode, your main structure is still going back and forth like this, but your tuned mass absorber is going in the opposite direction. And then in your other mode, your main structure is going back and forth like this, but your tuned mass absorber is going along with it in the same direction. So here I have two modes, and each of them are split to give you a total of 4 modes. So this is the model of the absorbed structure, and I have 4 modes here, and the frequencies are similar to those original modes. And you can see here, this is a great view of what I'm trying to achieve. The blade is hardly doing anything, but the tuned mass absorber, which you can see inside, is really moving like crazy in this mode also. Now, it's not really exiting the surface of the blade. That's just magnified by, I don't know, 100 or 1,000 times, just so that you can see it in the visualization. But it is moving an order of magnitude, 2 orders of magnitude more than the blade itself. And that's what we're trying to do. We are rearranging the structural dynamics. We're moving the energy from the airfoil, which is our critical part, into our tuned mass absorber, which is completely contained within the air, within a cavity inside the airfoil. In this mode, it didn't work so well. And you can see that pretty clearly. But it turns out that this mode was not effectively driven by the excitation that I applied to it. And that is my optimization, is trying to minimize the response. So whatever you want to achieve with your modes, that's what you're going to get when you do the optimization of the shape of this tuned mass absorber. Now here's the 4th mode, and again, you see how well it works. And you can see in this case how the tuned mass absorber is moving in the opposite direction from the blade itself. So the analysis, this is the key analysis for this tuned mass absorber. In this analysis, I applied a sinusoidal load on the top corner, called the leading edge pressure side of the turbine blade. And then I measured analytically, that is on a computer model, the response of that same point. So this is the x-axis here is the frequencies. So as you increase the excitation frequency, and that's what causes resonance, is when your excitation frequency is sitting right on top of a mode, and that's what we're trying to reduce the response when that happens. Well, in your baseline blade, that's the red here. So that says when you're vibrating at 7,300 hertz approximately, then, and you're sitting, when you excite the structure at that frequency, you'll get this response for your baseline blade without an absorber in it. And in comparison, when you put in this tuned mass absorber, if you excite it, well, actually, so that original one, you'd get a response here, and then at the second mode, which turns out to be way down there. So as I mentioned, it's not efficiently excited by this loading. And so the goal is what happens here with your tuned mass absorber. You have 4 modes, but the peak response of each of those 4 modes is way below the original baseline. It's a 60% reduction, actually, in your resonant response, your peak response. So that's the goal. That's what you're trying to achieve. So this was analysis. So then how did this work in test? And this would be for the prototype 3. Well, the first thing in the test was, and again, I impacted on the leading edge pressure side tip, and I measured the response with a laser scanning vibrometer, and I got the modes. So between my model and the experiment, there was very, very good agreement on the natural frequencies. And since the natural frequencies are key here, that's really important to get a good agreement. So the agreement was always within 2%. Now, And here is the test results. This was the test result for the baseline structure prototype, and this was the test result for the one with the TMA. Now, the initial reduction did not match the prediction. I actually only got about 31% reduction. And I was a little bit baffled by that. But then I went in and looked at the material damping on these two structures. And it turned out that because I didn't apply a standard heat treatment onto the structure, just because it was a prototype and I didn't anticipate that this would happen, well, that's more than likely the reason. Well, what happened was that the two structures cooled differently. And when they cooled differently, they gave you different material damping values. So what is material damping? That's just the damping that's inherent in this material. Well, it's a solid monolithic material, so you hardly have any material damping, which, and these are the values, 0.028%, that's correct, and 0.0156%. Now, these are next to nothing, but when you're comparing apples to apples here, then the original value that you're comparing is based on these values. So the original baseline magnitude, the only damping it's got is this little bit of material damping. So if you have a different material damping in your TMA blade, then the comparison won't be right. So to evaluate how this concept worked, I normalized the damping. If you do that, then the reduction is 62%, which is a great match with that prediction of 60%. So again, a really excellent result, 62% reduction in your response. So what are the benefits of this additively manufactured turbine blade tune mass absorber concept? Well, the internal tune mass absorber is very effective at reducing the peak response by up to 60%, and the test showed a similar reduction. So that's what you're trying to do. The design can be optimized for maximum energy transfer for specific modes, and that's because the damper, or not the absorber, is placed on a location on the blade where you have a lot of motion. Under platform dampers, which are basically every other damper except for maybe shroud dampers, are placed in locations where you have very little motion, so you have very little energy transfer. Now, this next one is a big deal to me. This structure and the model of it is entirely linear. You can model this structure with any standard finite element code, and the results that you get out of your model are the results that you're going to get out of your structure. So those results are analytically predictable. Right now, if you put a damper on a turbine blade, a damper, a true damper, you have to do a dedicated test program just for that specific design, for that specific turbine blisk or turbine or inserted bladed disc. And it's incredibly expensive. It's just a trial and error technique. You put it in a spin rig, you spin it up, you measure the response, and you say, oh, that didn't work very well. Let me try it a different way. So you tweak your damper a little bit, you spin it up, you test it, and you have to do that for every single different bladed disc that you've got. So it's incredibly expensive. Here, once you've proven out the concept, which I'll talk about in a minute, you don't have to do that anymore. You just model it on your computer, and what you model is what you get. So that's a huge savings in cost. One thing that's really cool is, unlike traditional dampers, which you have to build a bunch of little bitty dampers and stick in there, so that's a huge cost, there is zero additional fabrication cost when you implement these tune mass absorbers into this into a additively manufactured turbine blisk. The only thing you have to do afterwards is get an air gun and blow out the powder through the holes. So no additional fabrication cost. Another big benefit is that this unique design enables mitigation of any two modes that you would like. And that's because I have three parameters to work with here. on my tuned mass absorber. I've got the length of that banana shape. I've got the major axis, since it's elliptical, and I got the minor axis. So I can optimize. I just run it through an optimizer to optimize those three parameters to minimize the response in the frequency range of my two modes that I'm interested in reducing the response to. There are a number of other paperwork tracking is minimal, and that's just an advantage of blisks. It doesn't really hurt the centrifugal load capability. You might think you have a loss of cross section, but it's really actually quite small. And a big deal is that you could implement this concept not just on turbine blisks, but on all kinds of other structures as well in turbo machinery, static hardware, and other rotating hardware as well in the pump side, or in the static vanes or the static nozzles. Anywhere you've got a vibration problem, you could implement this. And finally, this technique, there are a lot of other additive manufacturing techniques in addition to the one I use. The one I use, you have to put it into a machine, which the size is a bit limited. But there are other methods. One's called directed energy deposit, which is you don't put it inside of a machine. It's big laser shooters are kind of on this external, and you can fabricate huge structures. At NASA Marshall, we're fabricating rocket nozzle combustion chambers using this technique. So it's got a lot of scalability. Now, one issue that's come up, there's a lot of concern in the technology, in the community, the turbo machinery community, about high cycle fatigue capabilities of additive manufacturing. And what I want to tell you is that at NASA Marshall, there has been a huge amount of research and development and testing on different finishing techniques for additively manufactured parts. And our folks have achieved something close to machine capabilities. This is what's called the SN curve, where it measures the maximum stress for a number of cycles. And it's the standard method for measuring high cycle fatigue capability. This solid line is the as machined capability. This dashed line is a new technique, a new finishing technique called low stress ground. And here's pictures of the finish. That's the low stress ground finish. So it's a beautiful finish, and it gives you high cycle fatigue properties basically at high cycles, which is where you're interested, almost the same, exactly the same as you would get from our material manual for machine parts. So in conclusion of my section, then we'll move on to the licensing section. An innovative yet straightforward turbine blade response reduction technique has been developed at NASA Marshall. And the additive manufacturing really enables this design. You could do this potentially in certain types of blade designs without additive, but additive certainly makes it a lot more feasible to have the cavity inside the blade and the absorber inside the blade. And this offers an effective and a predictable resonant response mitigation for any desired mode in blisks, with a huge savings in development effort and fabrication cost. We are seeking partnerships for licensing and for the development of the concept, and Jordan will discuss that a little bit. The options even start at just $2,500 a year. Now, the next step that I'm looking to is NASA has committed to funding the fabrication of two 20-inch Intraglybladed discs, or blisks, as shown here, with using this design. Well, one would be a baseline without an absorber, and one would have the absorbers in each blade, and putting them in a spin pit. And I've spoken and worked with folks at the Ohio State Gas Turbine Lab spin facility. And here's where you would put the installed rotor, and you spin it up, and they have a multitude of methods for exciting the blade modes as this thing is spinning. And so that's that would move this technology readiness level up to a 6 or a 7, a really good level. So that's all I have at the moment. Jordan, do you want to?
So if you have any questions that you can come up with later, feel free to email our agency licensing executive that he can route us to either myself or to Andy, and we can make sure we can answer any questions that you need. They're located right here at the bottom of the screen. It's agency patent licensing at mail.nasa.gov, or the phone number is 202-358-7432. And I just wanted to thank everyone again for spending your afternoon with us. And Andy, a great presentation as always.
Well, thank you, and thank you to everyone who attended.